Hello and welcome to another live session. Floor is open for your questions on astronomy. We'll keep up our live sessions during the summer. The frequency may go down slightly. It's hot. It's over 100 here in Tucson. Nothing moves or expends extra energy in the summer here. Even the lizards get a little ornery in Tucson in the summer, so maybe every couple of weeks, but we will continue through the summer and then pick up the pace in the fall. So anything you want to ask about astronomy, floor is open.
All right, so the first question from Gerald, who's on with us live, is while wearing solar glasses, can you look through binoculars to view the solar eclipse? If so, do the binoculars need some kind of a filter?
It's a good question because, you know, safety is paramount when it comes to solar eclipse viewing. And I'll just issue the standard reminder up front. Well, first of all, remember that that's how Galileo went blind, was by careless observation of the sun. And he was one of the best scientists of his lifetime. So even the best people can make mistakes in this regard. It really only takes a couple of seconds of unfiltered direct observation of the sun to damage the eye. So solar, proper eclipse viewing, solar filter glasses, get it from a reputable source, are fine for dimming the sun, basically taking down the radiation by several orders of magnitude, and sometimes filtering out the short wavelengths too. And if you have those glasses on, then anything that comes behind them is fine. So you can then look naked eye, you can look magnified through binoculars, because the protection is coming from the glasses themselves. But it's a good question. I mean, that does not extend to small telescopes, however, because then you're capturing a lot more light. Binoculars have a decent field of view and a modest magnifying power, but they should be safe.
All right, the next question is from Valentine, who asks, Hubble has inspired artists and people all around the world with its colorful and stunning images. Do you think that its replacement by the James Webb Telescope will lower the interest scientists have for astronomy-related matters?
That's an interesting question because, as the questioner alludes to, Hubble has carved out essentially a unique niche in the popular mind as far as beautiful imagery of the universe. As I think I've mentioned in answer to other questions on this subject, the Hubble project, their landmark images are in the Hubble Heritage Collection on their website, but there are thousands of others, of course. Those are just the best few hundred. Those were always done with an eye to scientifically realistic color, and of course beautiful color. So, painstakingly curated images, beautiful colors that are scientifically representative, if not 100% accurate. And that's a pretty hard bar to reach. A Hubble project also encourages collaborations with artists. So there are visual artists who've been associated with the Hubble project. Some have had small grants from NASA to pursue that work, and that involves altering Hubble images artistically or doing artistic visualizations of targets that Hubble observed with its cameras. So Hubble has encouraged this sort of artistic experimentation and the viewing of Hubble images as art objects. The James Webb Space Telescope is not the same kind of a telescope as Hubble. It's a bigger telescope with more collecting area, but it's somewhat tilted in its science and its capability towards infrared wavelengths. The redder optical wavelengths, but not across the full optical spectrum. So essentially, James Webb will take visible images of the universe, but it will be taking a lot more infrared images of the universe. It also doesn't have quite the resolution, because of the working at the longer wavelength. It is a bigger telescope, which speaks to higher resolution, but working at longer wavelengths gives you lower angular resolution. So many of James Webb's images will not be as absolutely sharp as Hubble images. So I think because of and also a lot of James Webb's science is going to be done with spectrographs rather than imaging cameras. That's also true of Hubble. Hubble has always had spectrographs, and a lot of Hubble science does not involve taking pictures. So for those combination of reasons, James Webb is unlikely to produce the iconic imagery that Hubble did. There will definitely be amazing images, and including images of things that Hubble couldn't see because they were too faint or too far away, too high redshift. But just in terms of the volume of lush, colored, wide field images, James Webb won't compare. And that last point is important, wide field. Hubble always had cameras which either from individual images or by mosaicing, so tracking across the sky and building up a larger image, could produce a huge landscape of stellar and galactic features. The James Webb is going to be more targeted. It's going to tend to look at smaller regions of sky, so it won't make these big sweeping panoramas of the sky. So for all of those reasons, don't expect the same from James Webb as you've expected from Hubble.
All right, our next question is, how useful will the International Linear Collider be for particle physics and understanding astronomy?
It's an important project. As to give the historical context, the United States sort of ceded leadership in particle physics in the 1980s when what was called the Super Collider, the SSC, which was due to be built in Texas. In fact, there are still tunnels in Texas, unfinished tunnels for that project. That project was defunded. It never got sufficient mass of financial support or congressional support to be funded. And the locus of particle physics moved to Europe with CERN, and most particularly in the last 5 or 6 years with the Large Hadron Collider. The International Linear Accelerator is an attempt, to get U.S. particle physics back to the center of the stage. It's not to say that American physicists are not enormously important collaborators on CERN projects, including leading some of the instruments at CERN, which detect the particles as opposed to the accelerator itself. The reason why linear accelerators are important is because they can produce enormous energies in short spans. I mean, well, short in the linear accelerator still means many kilometers, but the technology is not as tricky, as finicky as a circular accelerator. With a circular accelerator, you're having to use very powerful magnets to deflect the particles, because these are charged particles. And when you deflect them, they emit radiation, and so you have to accelerate them more. There are a lot of instabilities in trying to keep particles in circles aligned with each other as they race round and round a circular vacuum tube. So these circular accelerators, like the Large Hadron Collider, are extremely complicated, difficult, and therefore expensive to make. The linear accelerator, sort of archetype of a first powerful linear accelerator, is the one at Stanford, and the international one that's being mooted is just a supercharged version of that, is simpler because of the linear path, because the magnet technology is required to do extremely rapid acceleration up to close to the speed of light of these particles and very high energies, is possible. And then there's a fixed target. So they slam into a fixed target, whereas at CERN, you actually have to make counter-rotating particles, protons and antiprotons, for example, slamming into each other or into a fixed target. So this linear accelerator that's not cheap, but it's not as expensive as the Large Hadron Collider, is going to have a niche of particle physics that's quite important. And of course, American scientists are more prominent in that project than they are overall in CERN.
Great. The next question is from a live viewer, Rahul, who says, as we know, galaxies are expanding. I wonder whether universes are expanding or not in the multiverse proposed model. And really then, you talk about at what scale is expansion detectable? Galaxy, solar system?
Mm-hmm. So just to make a minor correction on the question itself, the galaxies are not expanding. So galaxies in our universe are held together by their internal gravity, which is mostly dark matter. So galaxies in the universe, all that we diagnosed so far, including our own, are about 80 to 85% dark matter, and the rest is normal stuff, hydrogen, helium mostly, of course, that we're made of. And all that matter distributed over the large size of the galaxy, including its sort of invisible halo, which is almost all dark matter, is sufficient to hold the galaxy together. So though the stars are doing elliptical orbits in the case of an elliptical galaxy, or circular orbits in the case of a disk of a spiral galaxy like our own, there's no net expansion. These orbits are stable and will continue without the galaxy sort of dissipating or changing shape. So galaxies are not expanding. It's on larger scales where we can diagnose space-time that is expanding. And it's this expanding invisible space-time that is mostly empty, of course. The gaps between galaxies are much larger than the galaxies themselves. That is getting bigger as time goes by, and it's getting bigger at a faster rate. So there's an accelerating universe, and that accelerating, expanding space-time is carrying all the galaxies further and further apart from each other. So that's the universe we live in, and that's a process that's been underway for almost 14 billion years. So the question also was about other universes and what's going on beyond our immediate space-time, and there, of course, we don't know. The multiverse concept is very hypothetical, has no evidence to support it, is attractive to some theorists, but not all. Postulates that because our universe had a quantum origin, there might be other universes, other space-times separate from our own that are out there that have their own properties and their own behavior. It's not clear that they would have the same behavior as ours. Those universes, depending on their constituents, depending on what kind of dark matter, normal matter, and dark energy they have, if those are ingredients that all universes have, may be expanding at a much slower rate, may not be accelerating, may be never have reached a very large size as our universe has done over a long period of time. So there are other possible behaviors of hypothetical other universes. But now you're doubly hypothetical because just the existence of other universes in a multiverse concept is not proven. So to go beyond that and to speculate what their behaviors would be like, and would they have Hubble type expansion or accelerating expansion due to dark energy or oscillating universes, another possibility from the 1950s, is really, far beyond what we can actually verify with modern science. So this is getting close to philosophy at this point, or speculation, rather than the kind of science that most astronomers do.
All right, the next question is from a live viewer, Paul, who asks, quantum theory states that a particle can exist simultaneously at different places. Can you explain this concept?
So quantum physics indeed says that particles are not localized. Because there's an underlying principle in quantum theory called wave-particle duality, where all the phenomena we observe to be particle-like in our universe, that is, objects acting like they were concentrated in space, carrying fixed energy from one point to another, can also be thought of as wave-like. Similarly, wave-like phenomena, including light, can equally be thought of as having particle-like properties, and that's why we use the word photon for the energy carrying entity for light. So basically every physical phenomena that we can identify has both wave-like and particle-like properties, and which of those is dominant, or which of those properties manifest as dominant, sort of depends on the experiment you do, depends on how you detect them or how you create those entities. And so in that sense, particles are not strictly localized. They're fuzzy, would be one way of putting it, and a maybe slightly more accurate way of putting it is you can think of a particle like a wave packet. So if you think of it in the wave paradigm, it has waves that are concentrated. Their energy is concentrated in a region of space, but there's no hard edge to that energy. The wave amplitude tails off in every direction so that it's not fully localized. And so instead of a particle having a probability of 1 of being in place X, a particle has a probability that's less than 1 of being in place X, and it has smaller probabilities of being in a slightly different place. And that's essentially true of all quantum phenomena, of every particle in the universe. The act of measurement also changes the situation of a particle, and that's part of the indeterminacy of determining the position of a particle.
All right, the next question from our live viewer is, do you have any theories on what is causing the recently observed dimming of Tabby's star?
So that's a hot topic. Tabby's star has a scientific designation, KIC, and then 7 numbers of phone number, like a phone number that I can't remember the digits. That's from its catalog. That's a Kepler catalog number, KIC. So discovered by Kepler in its search for exoplanets by the dimming, the periodic dimming of a star, this object leapt out for astronomers doing these searches because it had these extremely, most of the dimming eclipses from a Jupiter would be a 1% dimming, from an Earth, 1/100% dimming. These are very mild eclipses, and you'd be lucky to see a planet with multiple eclipses, although there have been a few. Well, this star showed dramatic dimmings by tens of percents in a very chaotic manner from apparently multiple objects passing in front of the star. And it wasn't truly repeatable. So the thing that immediately marked it out from the exoplanets that Kepler has discovered thousands of was the fact that the dimming didn't have the simple profile of a dark object, a dim object like a planet passing in front of a star and then doing it again one orbital period later and then 2 orbital periods later and so on. It had a much more chaotic trace. It involved multiple eclipses or dimmings, if you like. They were very strong, and they didn't repeat in a known way. There has been subsequent behavior because people have been looking at this star really hard, and of course the immediate speculation was this is these are artificial signals. This is an alien intelligence, some alien construction around a star. There's a concept that's almost out of science fiction, but is still out of science, called the Dyson sphere, named after Freeman Dyson, famous physicist who I think is still alive. He's 93 at Princeton, one of the great figures of physics of the 20th century. And so Dyson speculated about an advanced civilization that would build a structure close to a star and around it to capture a large part of its energy to then use to fuel civilizations that didn't have to be located right there. Now, it doesn't have to be a solid structure. In fact, it couldn't be a solid structure because it would break apart if it was solid. So it wouldn't be a totally filled in structure. And of course, immediately people connected the dots and thought, oh wow, this chaotic dimming of this star is a physical structure around the star, a Dyson sphere type object, and it's evidence of an alien civilization. It's one of their artifacts. Well, that's an attractive hypothesis, but of course, it's not been proven. In the intervening roughly year since this behavior was discovered, the SETI, the Search for Extraterrestrial Intelligence, astronomers have trained radio telescopes on it, and of course optical telescopes have been trained on it to actually look for artificial signals, to look for consciously constructed signals the way SETI does anyway, and nothing has been seen. So the SETI scientists are unconvinced that there's an alien intelligence at work. Meanwhile, astronomers have scratched their head to understand this behavior, and they simply, at the moment, are not sure because this is unprecedented behavior. The best guess at the moment is that these dips are caused by a swarm of exocomets, if you like, sort of cometary material, substantial cometary material that in the inner part of the solar system, perhaps it's migrating towards the star. So it's not in the normal, very distant place where comets are in our solar system. And as that swarm of cometary material crosses the face of the star, it would lead to substantial dimming in a sort of chaotic pattern because there would be multiple objects causing the dimming, and they would not necessarily be on a periodic orbit where the same pattern would repeat so many days or years later. That's the best hypothesis at the moment, but it's actually going to be very hard to show that that is the truth. However, I would say the bet on it being alien intelligence is a lower probability bet.
Right. The next question from one of our live viewers is also a bit of a clarification, I think. Will cosmic ray flux change due to the eclipse in August? And if so, how will it change?
So yes, when the sun is occulted by the moon, as in a solar eclipse, just due to the perfect coincidence that the sun and the moon, despite being very greatly different distances from the Earth, they're also greatly different sizes and a similar ratio, which leads each one to subtend half a degree in the sky, and so one can cover the other. And when, of course, the moon occults the sun, it not only dims its light, it also dims its high energy radiation. So yes, the eclipse has an effect on the cosmic rays or the high energy radiation from the sun, but there the nature of the effect is a little more subtle and distributed. When the light from the sun streaming from the photosphere of the sun, its cool surface at just under 6,000 Kelvin, takes essentially 8 minutes, 8 light minutes, if you like. That's how far away the sun is. So 8 minutes after the sun, the sun is dimmed, and the sunlight from 8 minutes ago that's dimmed, and then the moon crosses and the sun comes back up. Well, the cosmic rays and high energy radiation from the sun do not always travel at the speed of light directly. Sometimes they interact in the chromosphere. Sometimes they interact with the solar wind. They can be, and they're often particles that are not traveling exactly as fast as photons. So there's a more dispersed effect on the cosmic rays than there is on the light itself, which just dims and then returns in a very obvious way. But yes, the eclipse will affect all the radiations from the sun, not just the visible light.
Great. Our next question is, hello, Professor. I love astronomy and I'm very passionate about it. Currently, I'm a software engineer. What are some entry-level positions in astronomy for people like me to get into the field?
Well, there are definitely possibilities. It's a small field and it's a niche, but I mean, if you have a knowledge of astronomy, some training, and are a good software engineer, then essentially every major observatory, my observatory, Steward Observatory, operates telescopes on 5 different mountaintops around Tucson and on 2 different mountaintops in Chile. So we have a lot of observatories, but every major observatory employs software engineers because software is an amazingly important part of producing data from large telescopes. I've seen an estimate on the very big projects like the Sloan Digital Sky Survey. So these sort of multi-$100-million astronomy projects that suggest that if they plan the project without allocating about 1/4 of the budget towards software design, software engineering, and data pipelines, the project will fail because astronomy is so data-driven, and the data volumes and the complexities of the data are such that software engineering is extremely important. So your question is a good one because there is definitely a niche for that skill. So the combined skill of being a software engineer, programmer, with a strong interest and some knowledge of astronomy. You don't have to be an expert. You just have to understand what it is people do with astronomical data. Indeed suggests that there are job possibilities. The American Astronomical Society has an online job newsletter. Most of those jobs are academic, faculty, postdoc positions, but also there are engineering jobs listed there. And then the other place, of course, is just to go to the websites of the major observatories because the big ones are essentially always hiring in some capacity. And so if you just go to the Keck Observatory, the Gemini Observatory, Kitt-Peak, Steward, etc., you can make a list of the top 15 or 20 observatories around the world, and they are worldwide now. There's very likely to be at any given time a dozen, I wouldn't speculate on the number, but I'm going to guess a couple of dozen software engineer jobs at any given time. Some of these jobs are challenging because sometimes they involve work at altitude, sometimes they involve people willing to do shift work or work a week on, a week off, or whatever. These are not sort of always 9-to-5 jobs. And in fact, maybe some of the more challenging and fun jobs in this arena are not the 9-to-5 jobs, but they're definitely out there.
All right, the next question is, why do astronomers explain the universe as stretching when fragments in a 3D explosion also all move apart from each other in 3 dimensions regardless of their current position? What does stretching explain that a 3D explosion fails to, and what are the implications?
That's a good question because it's at the heart of modern cosmology of how we understand the expanding universe. So the aspect of an explosion that do not capture the situation of the universe we live in are the fact that an explosion is what a physicist would say a ballistic situation, where there's a point of origin of the explosion and then the pieces of the explosion, shrapnel, gas, liquid, whatever comes out of the explosion is moving apart, typically radially in all directions at a certain speed. Maybe the speed changes and it slows down, or maybe it's in a thin medium and so the speed doesn't change. But it's ballistic, and you can measure the motion of these ejecta, the ejected aspects resulting from the explosion, traveling through a medium. And whether the medium is air, I suppose it could be underwater, it could be through a liquid too, or it could be through the vacuum of space. But it's still got a reference frame. Even if the explosion happens in beyond the Earth, say somewhere between the Earth and the Moon, you can measure the movement of those fragments relative to the Earth, the Moon, the nearby stars, the solar system. So those are ballistic situations, explosions, a fixed point of origin, objects moving through a medium in a particular pattern. The universe doesn't show those attributes because what is expanding is space-time itself. And so to understand the universe, you go back to the theory that's at the heart of modern cosmology, which is general relativity. And Einstein's gravity theory postulates something called space-time, which is invisible. It has 3 dimensions of space, x, y, and z, and 1 of time, so it plays out in time. And in general relativity doesn't require the universe to be expanding. It allows for an expanding or contracting space-time, and it turns out by observation that our space-time is expanding. So the understanding of expanding space-time comes from general relativity. And in general relativity, it's what's called technically, to a mathematician, the space-time manifold, which is just literally the geometric construct of 3 dimensions of space and 1 of time, where the distance between any 2 points in the vacuum of space is increasing over time, without reference to anything else. And that's the critical difference between that and an explosion. The expanding universe does not require reference to an external medium. The expansion is not happening with respect to something else or anything else. It is indeed the entire universe that is expanding. All points in space are expanding from all other points in space. And that's a hard concept, but that's actually what the mathematics of the theory says, and so that's how we understand it. Now, space-time is invisible, and so we use galaxies, astronomers use galaxies as markers of this invisible space-time. And it's by measuring the redshift and the positions and sizes and so on of galaxies that astronomers get access to the expansion in all dimensions of this invisible entity called space-time.
All right, the next question is from Deanna, who's on with us live, who asks, is there any way to observe the effects of black holes here on Earth using, like, as a normal person, using a small telescope?
Not really. Black holes are rare. So first of all, black holes only result from the death of massive stars, and massive stars are much rarer than low mass stars. So the nearest confirmed black holes are distances of 40, 50, 100 light years. 100 is a typical distance where you might find a handful of light years, a handful of black holes. Well, there are thousands and thousands of stars closer than 100 light years from the Earth. So, and most of them are red dwarfs or dim stars. So black holes are rare, and the nearest are pretty far away. And so that's part of the problem, that when a star is 100 light years away, the size of that star, even if it was a normal star, 1,000,000 kilometers across, the size of that star is impossibly small, such that a telescope couldn't possibly see its actual size. Well, black holes are even smaller. A black hole is about 10 kilometers across. And so it's 100,000 times smaller than the sun, and it's going to be thousands or millions of times further away than the sun. So black holes would be impossibly small in the sky. And so you need pointers to them, and typically we only see black holes when they're in binary systems. So black hole detection and hunting is a really hard thing, and it took decades actually for us to just have a few dozen good black hole candidates. And a lot of the telltale signs came from X-ray astronomy, showing the enormous radiation that happens when gas is pulled onto a black hole by its companion and heated up into an accretion disk. So because of all these things, it's a really hard thing, say, for amateur astronomers or people with a small telescope to sort of get into, because the black holes are rare, they're far away, they're very small, they can't be directly observed, and even the indirect observation often requires techniques like X-ray astronomy, which is not available to most amateur astronomers.
Somebody has kind of a follow-up question related to the previous question that you answered, and it is, as space and time expand, or as space-time expands, does time become grainy, or is there any change in the resolution, I guess, of space or time?
That's an interesting question. Well, it's an interesting question about space too. are either space or time grainy in the space-time construct? And the answer, that's an interesting question because the answer is not entirely obvious. It's not obvious because general relativity is a smooth theory of gravity. When I said that space-time was a three-dimensional manifold, or the space-time manifold, the manifold is a mathematical term. It's used in geometry, independent of any physical theory or anything like space and the universe. A manifold is a way for mathematicians to describe continuously curved shapes, and the key there is continuously. So in the construct, in the mathematics of general relativity, space-time is assumed to be continuous. In other words, not grainy in space and not grainy in time either. And as it expands, it just expands. The scale gets bigger, the time flows by. There's no obvious changing of time unless you're in a strong gravity field. That's relativity would say that time would change in strong gravity. But in both cases, it's a continuous effect with no quantization and no graininess. But the reason it's an interesting question is because people are not convinced that general relativity is the final theory of gravity, because it is a continuous theory and because it does not take into account quantum theory, where matter is grainy. And actually, at root, time is grainy too, in the ultimate idea of nature. So there's a suspicion that space-time may indeed be grainy on very small or equivalently very, very high energy scales. And that's a speculation that people would love to confirm. There are very ambitious and interesting lab experiments, a couple I know of at Fermilab, that are trying to actually use desktop physics or lab physics to drill down into quantum scales to see if space-time is actually grainy. It's not an experiment you can do with astronomy, but it's an experiment you might be able to do with physics.
All right, the next question is, most of us are just curious about astronomy. Eventually, visual observers, most of us do visual observing using the visible spectrum. Due to light pollution, is it expected that the amateur astronomy community will have to shift to radio astronomy? And is it possible to practice radio astronomy with, say, old TV satellite equipment?
Yeah, it's a good question. I mean, it's kind of a depressing question to think that amateur astronomy will die because of light pollution. I think it won't happen. It is happening slowly. Light pollution is getting worse for sure. And if you look at the night sky map of the United States, for example, most places east of the Mississippi, it's really hard to find a truly dark sky. You can, but it's hard. West of the Mississippi, there's still some dark places. If you look at Europe, you can almost forget about it. There's some places in Eastern Europe, some poor Eastern European countries where there are dark skies. In Western Europe, almost none. So yes, light pollution is getting worse, and it's affecting amateur astronomers. But I think the impact at the level where amateur astronomers couldn't really do what they do is decades away. And for most people, a lot of amateur astronomers are retired people who've moved to places far from city lights. Nearby where I live in Tucson, there's a community called Portal, which is down towards the Mexican border, and it's a planned community of amateur astronomers where the house designs have little observatories built into the plan. I mean, it's kind of cool, and we have some friends who live down there. And so, there are places where you can still do very good dark sky amateur astronomy, and that's going to be true for decades. So it's not an imminent concern. But if you live in a big city, you may travel a long way to get to a dark sky. But the other part of the question is important too, because independent of whether the skies are getting too bright to do amateur astronomy, and they are, but slowly, radio astronomy is now open to amateurs in a way that it never used to be historically. For instance, as everyone knows, satellite dishes have reduced in size over a couple of decades from these sort of monstrous few meter up to 5 meter dishes that you used to see in the backyards of houses and businesses to small flat panel phased arrays. And a number of radio amateur astronomers got cottoned onto that really quickly. And so there's a lot of old satellite dishes that have been repurposed for radio astronomy, where they have a very decent collecting area and where the technology to put at the back end of the telescope to do radio astronomy is not that difficult to build or you can just buy it off the shelf for not too much money. So amateur radio astronomy, the bar has lowered on that to the point where there are hundreds of, maybe thousands of amateur radio astronomers worldwide, which is nothing compared to the hundreds of thousands of amateur optical astronomers, but it's a significant and growing number. And there's some very interesting things to do. Of course, you should know that the radio sky is getting noisy at almost the same or greater rate as the optical sky because of cell phones, cell phone towers, microwave transmitters and repeaters, and so on. So it's also getting harder to find places where the radio sky is quiet. And the only really way you get around that is going to either pretty high frequencies or very low frequencies.
Right, the next question is, what geoengineering strategies could be developed in order to make Mars a habitable planet? Would it be really possible to live there in the future?
I think we will be living on Mars. I'm making a pretty good bet that within 30 years there'll be a small permanent settlement there. Perhaps those astronauts will not live their whole lives there, but there'll be a permanent small settlement. And maybe within 50 years there'll be an independent permanent settlement where there's no resupply from the Earth, and those people form a community where they actually have children and live and die on Mars. But these are going to be in contained environments. The issue of geoengineering Mars so that the whole planet could be livable, because that's essentially what you're asking. It's the difference between living in some finite bubble domes where you harvest the soil to make oxygen and gather water. That's a very tractable problem. We know how to do that. Geoengineering the entire planet, we know how to do in principle, and it is possible. It's not, as they say, rocket science. It's not impossible technology, but it's on a scale where the cost and the time to do it is phenomenal. In simple terms, you have to somehow put enough energy into the Martian soil, particularly at the poles, to vaporize the frozen carbon dioxide and liquefy the frozen water. And by the combination of those effects and the energy you've deposited, raise the surface temperature by about 7 or 8 degrees Celsius. If you do that, then you'll start to set up a positive feedback loop where the carbon dioxide will continue to evaporate, where you'll continue to build carbon dioxide, and you'll get a greenhouse effect. So what you really want to do is put enough energy impulsively into Mars to generate some liquid water, which will not persist initially, but also enough carbon dioxide in the atmosphere to generate a greenhouse effect. When that takes off, then eventually you will, of course, bring the Martian surface temperature under a thicker atmosphere to above the melting point of water, and then liquid water can sit on the surface. And at that point, game on. At that point, you're within sight of creating a habitable, livable planet. Not at all for humans, because you still don't have oxygen. You'd have to seed the surface with microbes, oxygenating microbes, to gradually build up the oxygen. But you would have created a place where microbial life, extremophiles, could live across the entire planet. So that's the sort of strategy, but it's a very long strategy. We're talking trillions of dollars in a couple of centuries, I think, those are the lowest numbers I've ever seen for geoengineering Mars.
Right, the next question is, can you clarify the difference between the age of our universe and the size of our universe?
Yes, I think the question is getting to an interesting issue, which is that the age of the universe, just under 14 billion years, 13.8 billion years, is almost a factor of 3 smaller than the distance to the edge of the observable universe, which is about 46 billion light years in any direction. So a diameter, if you like, of 92 billion light years. So begging an immediate question, if the age of the universe is 13.8 billion years, how can the distance to the observable edge of the universe be 42 billion light years, which implies 3 times more time, 3 times more age? Surely that doesn't work. And it doesn't work if the universe could only expand subluminally. In the cosmic expansion, any 2 points in space we're moving away from each other faster than the speed of light for a good fraction of the age of the universe, about a third, the first third of the age of the universe. So you have the situation where after 14 billion years of evolution, there are points in space that are separated by substantially more than 14 billion light years, almost 3 times as much. And it's a reflection of the fact that the universe was expanding faster than the speed of light early on. And that raises also an immediate objection that can be answered, which is, how can that be possible? Didn't Einstein say nothing moves faster than light? And yes, he did in his special theory of relativity, involving sending light signals between observers or from one place to another in the solar system or in the galaxy. But Einstein's theory of general relativity, which describes the expanding universe, has no speed limit built into it. There is no limit on the expansion rate of space-time in general relativity. And so it's consistent with the theory, and it's completely consistent with observation, that the universe was expanding faster than light for some fraction of its history.
All right, the next question is, can supersymmetry be astronomically verified?
That's a good question. Supersymmetry, just to back up, supersymmetry is an extension of standard particle physics that tries to resolve the fact that there are different types of particles, that there are fundamentally different types of particles. There are bosons, which in quantum terms have integer spins, and these are typically force-carrying particles. So photon is a boson, for example. The particles, the gluons that carry the nuclear force inside the nucleus, are bosons. So there are these integer spin force-carrying particles, and then there are what are called fermions, bosons named after an Indian physicist of the 20th century, and fermions named after Enrico Fermi from the mid-20th century. The fermions have half-integer spin in quantum terms, and they're more familiar particles like electrons and so on. Now, these seem to be quite different types of particles, and in physics, that's a conundrum. Why do you have these quite different entities? Supersymmetry is an attempt to say that they are really manifestations of the same underlying uber particle, if you like. To make the symmetry work, and it's supersymmetry because it really applies to all the particles and forces we know about, to make this symmetry work, you have to postulate a sort of set of shadow particles. So all of the bosons have shadow fermions, and all of the fermions have shadow bosons. And in the nature of supersymmetry, these shadow particles, which haven't yet been observed, will tend to have quite large masses or energies. So they're kind of hard to produce or see in nature. To get towards the question, the best and quickest way to show supersymmetry exists is to detect these shadow particles with an accelerator, like the Large Hadron Collider. And that was indeed one of its primary goals when it was upgraded in energy, was the hope of seeing supersymmetric particles. It hasn't seen them, and so certainly the door is open for people to think of clever astronomical experiments for seeing supersymmetry. But really, to answer the question, there are no convincing astronomical experiments to detect supersymmetric particles. You really need such highly controlled circumstances to sort through the particle soup of things that happen at high energy in the universe, that astronomy is kind of too blunt a tool for diagnosing supersymmetry. With the Large Hadron Collider, even though it seems kind of random, you're hurling things at each other and looking at the debris that happens, it's actually a very highly controlled experiment where you have enormous precision of looking at what comes out. So colliders like the LHC are still by far the best way to show supersymmetry is accurate, or perhaps to prove it wrong. Astronomers haven't figured out a way to either demonstrate supersymmetry is correct or to prove it wrong.
All right. So the next question is, I think, needs a little bit of clarification about the difference between gravity and gravitational waves. But the question is, gravitational waves propagate at the speed of light. So the Earth isn't being attracted to this real-time sun, but rather an old version of it. Does this lag also happen at an atomic scale?
So there's sort of two questions here, or there are two issues here. Gravitational waves, remember, are a prediction of general relativity based on a gravitational situation changing. So a change in the mass or the configuration of mass in some astronomical situation. So when you form a black hole, that's a dramatic change in mass configuration. When black holes merge, it's the same thing, and so that produces gravity waves. And gravity waves, in the theory, propagate at the speed of light through the universe. So a signature of this change in gravity will propagate through the universe at the speed of light. In addition, in the theory of gravity and general relativity, the gravity force itself is assumed to propagate at the speed of light. And the particle that carries the gravity force in particle physics terminology is a graviton, a spin 2 particle, a boson. Graviton has never been observed, and there has never, despite some very ingenious attempts, been a convincing demonstration that gravity propagates at the speed of light, even when nothing is changing. Like, does the gravity of the sun take 8 minutes to reach us just like its light does? Pretty simple question, very, very hard to answer. Why? Because, of course, you can't turn off the sun's gravity. You can't turn it on and off or change it in any way. So how can you do the experiment? Whereas, of course, you can block the sun's light with an eclipse or other method. So you can show how fast it takes light to move through the universe. So the answer is these are suppositions of general relativity that really haven't been properly tested. And they're extremely hard to test just because you can't switch gravity on and off like a switch.
All right, the next question is, what type of technologies are being developed or considered to improve equipment being sent into space? What can be done to achieve faster rockets and probes?
So, rocket technology evolves fairly slowly. As you know, we're still using, chemical fueled rockets that could be solid or liquid fuel. The biggest bang for the buck, or the biggest punch per kilo in rocket fuel is a chemical called hydrazine. It's extremely volatile and unstable petroleum distillate, that we've known of for probably a century. And that's the kind of fuel that's still used in solar system probes. And that's about as efficient as you can get from chemical means. But essentially all of our rocketry on Earth and around the solar system is using chemical rockets. The exception, of course, to that is and can be solar sails, which are very sort of light sails, as large as you can make it and as light as you can make it. And of course, since photons carry momentum, the momentum of solar wind particles and also solar photons will be imparted to the sail and give it an impulse in a direction away from the sun. So solar sails have been used and prototyped, and there's some ambitious ideas for solar sails. That's really the only major technology shift on the horizon in the solar system. And of course, that doesn't really help you far from the sun. It's not going to help us in the outer solar system because the solar radiation gets so weak that doesn't provide much of a kick. So outside of those, the techniques of using nuclear explosions, nuclear fuel, which in principle is hundreds of thousands or millions of times more efficient than chemical fuel, we really don't even have a prototype of nuclear rockets. The designs have existed really since the 1950s. None of them have ever been built in space or tested in space. There are sort of safety, environmental issues with using nuclear fuel in space because these would be fission powered, and so they would have radioactive material involved. So you could sort of look at it and say, wow, things are going pretty slowly. We haven't really changed our technology for the last 50 or 60 years, and you'd sort of be right. So there are think tanks and prototypes and design studies and engineering studies, but as far as prototyping new forms of rockets in and around the solar system, not much is happening right now.
All right, the next question is from Paul. If dark matter is composed of the elements found in our universe, why does it not provide us with some visible UV, infrared, X-ray, or other radiation?
It's a good question, and in fact, the supposition by inference is that dark matter is not composed of the ingredients of the rest of the universe, or the elements, if you like, of the rest of the universe. So the material universe that we're familiar with is made of protons, neutrons, and electrons. Protons and neutrons, of course, are made of quarks, but we see the protons, neutrons, and electrons, and comprised in different packages, they form the elements of the periodic table. Dark matter is something entirely different because we know that it is not made of those ingredients. In fact, there's evidence for dark matter that's provided in many directions, primarily now by gravitational lensing, which weighs all the material, regardless of whether it shines or not. But as a corroboration that most of this material cannot be the normal stuff that we're made of, we have the theory of the Big Bang. The Big Bang theory includes a component of nucleosynthesis. So the Big Bang theory talks about where the material content of the universe came from, originally from pure energy. And it predicts how many normal particles there should be in the universe. And it's the number of normal particles we observe. So we get a cross-check with the Big Bang theory based on the normal matter we observe. And then, in addition, we infer 6 times more mass in a dark form. And so we know it's not neutrons, protons, and electrons. It's not the normal stuff, and therefore it's not elements in the periodic table. The current supposition is that it's a new type of fundamental particle. That's a prediction of extensions of standard models of particle physics. There are a couple of candidates, and people are looking really hard for those particles in a series of experiments down mines where they're shielded from cosmic rays, because it's very delicate work. Because the dark matter doesn't interact with electromagnetic radiation, it doesn't scatter light, emit light, or absorb light, which really limits your options for detecting it. So most of these experiments to detect the omnipresent dark matter, 6 times more than all the normal stuff, are to have a large solid-state detector made of germanium or silicon, ultra-pure semiconductor, typically, often very cold, shielded from cosmic rays in its own containment. And you're looking for the dark matter particles that are essentially moving through the universe at nearly or close to the speed of light in every direction. You're looking for those dark matter particles to interact with the detector and basically just create a mechanical resonance with the nuclei of the atoms in the semiconductor, and then you measure that collision essentially. But no light is emitted or absorbed because they don't interact with radiation. That's a very hard experiment, and people are trying to do it because it's the best lead as to finding out what dark matter actually is. I'm probably going to have to...
Okay, so then that's the last question we have for today.
Okay, thanks very much, everyone.